So just say hello to a few. Dale, Mr. Faulkner there. Raiko, nice to see you. Jochen, haven't talked to you for a while. Miriam, Carmen's here. God, there's a bunch. Great. Well, thanks for coming. We've been starting to promote and do these more and more often now, and are enjoying it. You know, I think a lot of us miss the opportunity to travel and go to conferences and see technical papers or technical presentations, and so we're really hoping to create this as an opportunity both for us to do these, and we recently hosted one of these. Melvin, you're upside down, man. Anyways, we recently hosted one of these with another company, Zimco Instrumentation in town, put on a webinar through us for one of the level technologies that they work with. And we're hoping we're going to be able to do this more for people. We're trying to make that Making Measurements Matter site be a place that people can advertise webinars, and we can start to try to bring our whole community back together a little bit and get people talking a bit more. Without much further ado about that, today we're going to be talking mostly about these guys, ZEGAZ Instruments, and the unique technology that they use for doing water and hydrocarbon dew points. It's really interesting. Chelsea's also works on branding and is working on our website. And one of the questions she asked me was, you know, tell me why you sell the products you sell, and sort of about each of them. And so it was an interesting thing to think about, you know, why did we end up working with ZEGAZ? They have a very unique technology, probably the only one that can do water and hydrocarbon dew points at the same time, that they can really separate those two dew points. My background's a spectroscopist. They're a spectroscopic based technology, so that appeals to me. And they're fairly low. We really look for technologies that are going to be low maintenance devices in the field. And so that whole combination of things really came together in the ZEGAZ technology for us. And so we were very thrilled to act as their representative in Canada. So our plan today, I'm going to talk a little bit about who we are, who Insight Analytical is, and kind of what we do. And then I'm going to talk about ZEGAZ and really how that technology works, and what the unique capabilities are. Sorry, just a quick couple admissions into the room as well. Scotty, if you can keep an eye on if anybody shows up on that waiting list to pop those guys in. I'm going to talk about the ZEGAZ instrument and what it does and how it works, and then to give you a little bit of an overview of the other products that we work with as well. So as far as Insight Analytical, we're a Calgary-based systems integrator and distributor. A lot of us came from the Western research background. A lot of my staff came in from the Western research background. So we bring a long history of working on process analyzers and process instrumentation to the oil and gas sector. And what Insight set itself up to do was originally a technology called JP3 Measurements out of the US, kind of spawned us because I was doing consulting work with them. And we started out selling that technology and then just started to add in things that we felt was going to bring value to the oil and gas sector. At the same time, we operate as a systems integrator. We operate out of a 20,000 square foot facility, 9 bay doors, full 10-ton overhead crane. We can lift a full analyzer shelter off the back of a flatbed, drop it inside the building, do all of our integration work, and then put that right back out to the onto the flatbed again. We're AB 83 compliant. For those of you from Canada, that's going to make a difference. In Canada, we have a thing called CRN numbers. It's kind of like the equivalent of the European Pressure Equipment Directive, and it relates to being certified for use on pressurized systems and vessels. And so we're able to build systems with full CRNs. We delivered systems for Alberta, BC, Ontario, Saskatchewan. We manufacture those right here in Calgary, ship from Calgary, run service out of Grand Prairie, Edmonton, and Calgary itself as well. I pride ourselves on our ability to do docs and drafting. A lot of the people, again, that worked with me or have worked with me before, our draftsman has been doing analyzer buildings and analyzer installations for 35 years. Shai, who works with us, does our docs. She does a fantastic job. One of our first projects was with a big engineering company. And, you know, big engineering companies would have a lot of documentation requirements. And we did an exceptional job, even they said so. Journeyman electricians, full factory acceptance test done right here in Calgary. On that integration side of things, we'll do everything. These are actually some small regulator panels we were doing for Carmen's on here, TC Energy and Coastal Pipeline. We did all the sample systems for the analyzers going on the Coastal Pipeline. We've done oxygen analyzers. This is a Barbon oxygen on a panel for doing oxygen in water. Full composite samplers. I just did a webinar recently about composite samplers. It'll be up on YouTube probably in the next week or so. But we do full composite samplers for liquid hydrocarbons in the oil and gas industry. When we do systems like that, we try to make sure these things are as operator friendly as possible. So if you go back and look at that composite sampler, you'll see on the back of it, there's a set of instructions right here. And down here is where this color-coded valve assembly is. So a lot of us come from having some field experience. And we know that when you get out in the field and you're going to do a task that you haven't done for a while, or maybe you've never done before, you want to have that ability to be able to do that task as easily and as simply as possible with a good set of directions there. So we try to incorporate that into a lot of the things that we build. Just going to erase my ink on here for a second. Oops, erase all ink. Okay, there we go. Oh, here's Saurabh is joining us. Just going to wait for Saurabh to join in here. Saurabh has just joined us. Saurabh is actually the president of ZEGAZ, and so if any of you ask any really hard questions, I'm just going to direct those over to Saurabh and make my life easy. But talking a little bit again about the systems we integrate, when we put together systems, we try to make them as operator friendly as we can, and that'll include things many times like color coding valve handles, putting directions right on there, using valve handles of different shapes. It enables us to write procedures and directions that make it really easy for operators to follow and be able to use equipment. So we'll go from systems like that. This is a near-infrared analyzer, near-infrared optical bench, spectrometer bench over here on a crude oil blending skid. So we have crude oil flowing this way, flowing through this skid. They're blending butane in, and we're using this guy to measure vapor pressure. Doesn't write so good there. So it's an RVP analysis. So we do a real-time vapor pressure analysis for crude oil blending. Get rid of some ink here again. We'll do full analyzer buildings. Again, these are two sample system panels. There's actually some automated grab sampling going on there. Flow control for the fast loops, full PLC controlling everything inside of a full building from the exterior. We'll do, again, near-infrared spectrometers, PLCs, automated grab sampling stations. In the previous presentation I did on composite samplers, we also talked about automated grab sampling. So we'll put in the capacity to be able to fill a cylinder whenever we need to and use that either for verifying that a product was off spec, for helping to build models for an inferential analyzer like a Raman or an NMR or a near-infrared analyzer, or just automated sampling because people say, I don't want my operators to have to go up and pull samples. One of my favorite pictures, this is up at a Kira facility, has two of our composite samplers in here. There's that same bench with the near infrared and all that automated sampling going on there. Condensate's often very waxy. So in the back over here, we've got a toluene tank that we do an automated solvent flush of the entire sample systems. So again, we try to automate as many of these things and make them as operator friendly as we can. So now I want to talk a little bit more. That's a little bit about us. Now let's talk about the important guys. I want to talk to you more about ZEGAZ and about dewpoint measurements and what they do that's really unique about it and what the results of that analysis can give us. So first of all, I want to talk about what is dewpoint. Then I'm going to talk about the specific methodology they use. And it's a very unique methodology. I'm going to show you some bits and pieces as we go along. So first of all, we want to consider what is dewpoints. What do we mean by a dewpoint? We see it commonly. This is fantastic weather for it we're getting right now in Calgary. We get a warm, humid day, things cool down at night, and dew forms on the grass. The air has been holding a lot of water vapor. As it cools off, there's a phase change, a phase transition, and some of the vapor phase moisture condenses out as a liquid. We think about dew points often in terms of water, but hydrocarbons, anything that actually can condense, is going to have a dew point temperature. So the dew point temperature is the temperature at which a gas undergoes a phase transition to drop out the first drop of liquid. If it's really cold, it may come out as ice instead, and we'll call it a frost point. The dew point temperature is dependent on the pressure of the gas, and it's also dependent on the nature of the gas, the chemical composition. So those are going to determine what the dew points are. So we want to understand how those affect dew points, especially for us in the natural gas industry. There's specifications on water content, and that's there because of a fear of hitting a water dew point, as it can cause corrosion. And there's also specifications on hydrocarbon dew points. And so we want to understand what we mean by dew point, and then how do we go about measuring it. So the first thing that we want to talk a little bit about is this idea of doing a phase transition. So we see phase transitions commonly when we look at things like phase diagrams. Phase diagrams are a graphical or a pictorial representation that shows how the physical properties of a fluid change as the pressure and temperatures change. They can show three different states: gases, liquids, and solids. Commonly in the hydrocarbon industry, we look at the phase diagram in terms of what's happening between the gas and the liquid states. When we're dealing in the hydrocarbon processing industry, we rarely concern ourselves with solid phase materials, at least on the pipeline side of things. Hard to pipeline solids. Phase diagrams give us a lot of useful information. So I'm going to show you an example of one here. If we have a natural gas mixture, so this is typically things like C1 through C9 hydrocarbons. Methane, ethane, propane, butane, pentanes, hexanes, heptanes, octanes, nonanes, things like that. We've got all these hydrocarbons mixed there. The heavier ones want to be a liquid at room temperature. The lighter ones want to be a gas at room temperature. And when we mix them together, we get a behavior that's the result of that combination of things being there. So if we're really warm and at low pressures, everything's going to be a gas or a vapor. So if our temperatures are high and our pressures are low, we're out here on the vapor side of things. If our pressures are really high and our temperatures are low, we're over here on the liquid side of things. If we were to take some of this liquid and start to heat it up, we would hit, actually I don't want to be up there where the, if we were to take some of this liquid and heat it up, we'd hit a place where we actually hit the bubble point. This would be where the first bubble of gas shows up. So the phase diagram lets us determine, well, where's our first bubble of gas going to show up? If we started out here as a gas and it was nice and warm, and we started to cool it off, when we hit this piece of the curve, we hit our dew point. So this is where the first drop of liquid hydrocarbons come out. If natural gas only concerned hydrocarbons, that would be the only dew point we would have to worry about. But our natural gas is a mixture of hydrocarbons and typically has some water vapor present as well. So as a result of that, we have two dew points we need to consider. If we look at this particular case and we cooled this gas off, we would have hit the hydrocarbon dew point at about 30 degrees F. And if we cooled it off more at about, I'm not sure what that number is, maybe 25 F, we would hit the water dew point. So we have two different dew points to concern ourselves with here. Depending on what pressure we're at, might change which dew point we hit first. If we had been at higher pressure up here and cooled this gas off, we would have hit the water dew point first and the hydrocarbon dew point later. So in a pipeline application, we want to prevent getting to dew points, because if we get liquid droplets into things like compressors, they're not good. Liquids can potentially cause more corrosion in pipelines. Liquids can also, if we drop out some of the heavier hydrocarbons, it's going to reduce our BTU values. So all of these things are going to affect our pipeline performance and our ability to do measurement. So ideally, we'd like to be able to know the water dew point and the hydrocarbon dew point as two separate values. So the hydrocarbon dew point is the temperature at which the first hydrocarbons condense out. It depends on the gas content and particularly the heavier components. So this makes it difficult. People sometimes think they can do this with a gas chromatograph. But the problem is those heavies might be there at very low concentrations and difficult to detect. So if we've got a lot of heavier components there, those are really going to affect our dew points, and they would have to be measured very accurately. Even if they were measured accurately, we would need a really good equation of state. Equation of states define kind of the physical changes in a fluid as temperature pressure changes as well. A lot of us have heard of the ideal gas law. Well, things aren't really ideal. So we often need a more complex equation of state. And if we use different equations of state, we can calculate different dew points. It's why it's so important we actually measure the dew point. So it's a function of the chemical composition and it's a function of the pressure, and we can't accurately calculate it by just doing a GC analysis. We actually are much better off if we measure it, because the GC analysis, if it misses some of the heavier components, is going to calculate a grossly incorrect dew point number. There's a number of reasons we want to do this. Operational reasons, we can do damage to equipment if we get condensation in it. Can cause problems with our flow measurements. It can cause issues. We're going to build up if we hit dew points, we build up liquids inside the pipeline, and these can cause us to have to do more pigging operations, cleaning out the pipeline. There's safety related issues. Certainly with water, we worry about hydrate formation. Natural gas hydrates are like an ice crystal that can form in lines. And this can cause blockage, cause flow restriction, reduce our flow rates. This has been really important to us in fields like the Montney. Even in a lot of this shale gas. The shale gas that's getting produced from these really tight formations is really rich. So it has a lot more hydrocarbons in it. And as a result of that, depending on how well the facility is doing its hydrocarbon removal, we can see heavier gases, more of this hydrocarbon dew point causing materials in there. They also add a lot of BTU value. So if we have too much liquid or too much heavy hydrocarbons, we can have issues with determining the right oxygen ratios for compressors and burners. And so companies like GE that do turbines concern themselves with what's the hydrocarbon dew point. I don't want to get liquids coming into my compressor lines. Same with Europe. Europe has a big concern about it for furnaces. Furnaces in homes. You don't want to hit a hydrocarbon dew point because it can block the jets. Custody transfer and calculations, hydrocarbons are going to affect our BTU. And so now also if we get hydrocarbons dropping out, we report low BTU numbers. So there's a bunch of good reasons for why we want to do dew point measurements, both for water and for hydrocarbons. We hit hydrocarbon dew points in operating facilities for a number of different reasons. We can hit it operationally, so have problems in the plant. We can also hit dew points by how we're doing our sampling, and that'll bias our results. Remember, if we're going to do any kind of sampling, we want to get a representative sample. If we have some liquids drop out, that sample may no longer be representative of what was in the process pipe. So the liquids may be present already in a pipeline or be created during a pressure drop or during a pressure increase. And so if we're sampling, using the right type of probes and probe installations is going to help us to get a better sample out of these systems. Liquids can be created by increasing the pressure. We compress, just like if you run an air compressor at home. You run an air compressor in your garage, you bring in ambient air, it's got moisture in it, you compress it, and liquids drop out, and you have to drain water out of the bottom of your compressor. It's been a really warm couple of weeks here. We're having to drain our compressor every couple of days. Liquids can be created by decreasing the pressure. We get a Joule Thompson effect, adiabatic cooling. And so when we, adiabatic cooling, we get this Joule Thompson effect. The gas cools as the pressure drops. So we go across a regulator, the gas cools, can condense out liquids at that point. When we cool it, we get temperature reduction. And of course, like I said, the JT effect is both a combined pressure and temperature reduction. So I'm going to kind of show a little bit about each of these because we want you to understand why this happens and why this is of concern to us in pipelines and in sample systems. So one of the ways that we can cause a dew point to occur is by compressing the gas. So if our gas was down here at some lowish pressure, and we compress it. As we compress it, the P2, we move into inside this part of the phase diagram. We're in a two-phase region. And this means that we will have hit the hydrocarbon. In this case, we'll have hit the hydrocarbon dew point. If we continue to compress this, we actually can hit the water dew point as well. So when we're on a low pressure wellhead or we've got casing gas, it may all be in the vapor phase. We try to take that gas and put it into a pipe to send it over to a plant, put a compressor on it, all of a sudden we can hit a dew point. We can also hit a dew point by reducing the pressure. So from an operational perspective, we could have a hydrocarbon that is sitting up here at high pressures, and we lower the pressure either due to pressure drop loss along the length of the pipeline. So as the pressure drops and we go inside this two-phase region, all of a sudden we get liquids dropping out. Or we reduce the pressure when we hit city gates. When we hit a plant, when we bring natural gas into the distribution grid inside of a city, we always lower its pressure. And there's a risk there when we lower that pressure, we may hit a dew point as well. When we're pulling samples or running analyzers, we often reduce that pressure. Most of our analyzers, such as gas chromatographs, laser-based analyzers, lead-acetate tape analyzers, they all run at typically atmospheric-like pressures, at most maybe 1.5 bar. And so when we do that pressure reduction stage, we have to be very careful when we reduce that pressure that, again, we don't hit a dew point and cause some of the things that we want to measure to drop out. If we were to do this pressure reduction, and here we would start to drop out water, here we would start to drop out hydrocarbons, it'll cause us to read low on the hydrocarbon content, low on the BTU value, low on the water dew point. Suddenly our system becomes dependent on what temperature or pressure we do the measurement at, and not on what's actually there in the physical composition. Again, the common one that we see when we think about dew points is if we lower the temperature. We cool a gas down and things condense. So during operations, if we're taking things like the overhead gases off of a condensate stabilizer or the overheads off an inlet separator, and we let it cool as it moves through the plant, we can get liquids dropping out. This can happen at wellheads. It can happen just because of cold pipes due to ambient temperatures. So operationally, this can happen within our facilities, and during our sampling, it can happen as well. Take warm gas and hit a non-heated probe. We were just out at a facility, and there's heat trace sample line, and then the probe body was sticking above the pipe. And when we see that, now that probe body potentially is cooler than the heat trace line, cooler than the pipeline, and becomes a place for things to potentially condense out. If we run these things through non-heat trace sample lines, people think they can just insulate a line. Works well with liquids. With gases, there's so little heat capacity there that if it's cold outside and you insulate that line's going to get cold too. There's not enough heat capacity in gas transfer to keep lines warm, even with adequate insulation. Same thing can happen when we pull a sample. If we have a cold cylinder, it's been sitting in the back of our truck, we go and pull a grab sample of that gas, we let it hit the cold cylinder, we'll condense liquids in that cylinder, then put gas in on top of it. And when we take it to the lab to do the analysis, it'll read high on liquids content because we condensed some of the liquids out in the cylinder while it was cold. Joule Thompson effect of this adiabatic cooling, when we lower the pressure of a gas and let it expand, it cools off. And so now we can both lower the pressure and cause it to hit a dew point, and the cooling causes it to hit a dew point. So this can commonly happen when we put a regulator in our sample systems. And so we have to be careful to use heated regulators and apply some external source of heat if we want to get a good dew point measurement. So if we want to get a dew point measurement, how do we do it? The Bureau of Mines method, the standard method, has always been to use a chilled mirror. Cool down a surface, monitor its temperature, and watch until you see condensation form on that surface. And really what ZEGAZ has done has taken that methodology, automated it, and used spectroscopy to make it be specific between water and hydrocarbons. A skilled person using something like an optical chilled mirror technology can look at the mirror surface, and on the shape of the ring that you get on there can determine whether it's water or hydrocarbons. What ZEGAZ has done is automated that, and they've done that using a technique that they refer to as CEIRST. I'm going to explain what that acronym means on the next slide. But it's a spectroscopic detection of the condensation. It uses different wavelengths of light to differentiate between the water and the hydrocarbon dew point. The other thing is it uses a crystal. It doesn't use a metallic mirror. And that's important because metallic surfaces can corrode over time, can get contaminated easily. And so by using a crystalline surface, we have an advantage in that it doesn't get attacked by the materials. In fact, the crystal that's used is synthetic sapphire. And if I do this, let's see, I'm going to show you one here. You can actually see this is the glass-like looking piece on top of there is the crystal. And so this metal block that it sits on gets cooled. As that block cools, the crystal cools, and that synthetic sapphire surface. So the second hardest thing next to diamond, doesn't get scratched, very chemically inert, used to store things like acids and things like that. This is the surface that cools off and liquids will form on there. So the way it gets put in is we have a small cell that goes over top of it. Gas can flow in and out, touches that cooled surface, and then we watch for condensation on that surface. I can explain a bit more. Oops, I went too high there. There we go, that's better. So basically that's our little cell. We flow in and out of it. On that surface, the condensation is going to occur. And when that condensation occurs, now we have to have a way to detect it. And that's where this chilled evanescence infrared spectroscopy comes up, the CEIRST method. The chilled, because we cool the mirror or cool the surface. Infrared, because we use infrared light at different wavelengths to tell the difference between water and hydrocarbons. And then we're going to talk a little bit about what this evanescent part means. There's a thing called an evanescent wave. When light bounces off of a glass surface, it bounces back off because of the change in refractive index. And it can actually go through the glass and hit the air on the other side and bounce off there as well. But it has to go out a little bit to see that the refractive index has changed. And we call that the evanescent wave. It interrogates the medium on the other side of the crystal and says, oh, I can't really go there. So we use this thing called an evanescent wave to make a little penetration out into the fluid that's on the surface and determine whether it's a hydrocarbon that's there or whether it's water that's there. We make all these measurements at line pressures and at line temperatures, or at line pressures, and we cool the gas from line temperature, and that ensures that we don't get phase changes before we get to the detector. In this technology also, we don't rely that the light beam can pass through the gas. It only goes through the crystal and then barely touches the gas. So this is kind of a drawing to kind of show what happens. Pick different colors of pens here. We have two beams of infrared light. They come up to the surface and they bounce off the crystal surface. And they bounce a couple of times and they make their way over to the detector. So there's beam one. Use purple for the other one. Here's my second beam of light. It goes and it bounces and it hits another detector. So the light's bouncing off the surface of this crystal from the inside of the crystal. So the light in this case is coming from the back side of this and bouncing off the facets of this crystal. As we showed, it sits on this block that's attached to a thermoelectric cooler. We cool that block. When the light bounces off the surface, there's actually a little bit of the wave that goes out into the fluid above it. It bounces off the surface because it's coming in at what's called the Bragg angle, and that's where the change in refractive index causes it to go back inside. In order for it to determine there's a change in refractive index, the wave actually has to go outside the crystal a little bit. In spectroscopy and infrared spectroscopy, we use this technique to make what's called attenuated total reflectance cells, or ATR cells. And in this case, we're using that thing, that evanescent wave, and it goes out and it touches the media above there. If it's all gas, it just bounces back in normally. As we cool the crystal and liquids start to appear on the surface, now that wave touches the liquids. So now it gets to interrogate the fluid that's above the crystal. And when it does that, we use two different wavelengths of light. One of them that is going to get affected when there's water there. The other wavelength is going to get affected when there's hydrocarbons there. So we have these two beams that are going out. Each one of them goes and gets to interrogate the fluid that's dropping out on the crystal as it cools. And one of the beams detects whether it's water, the other one detects whether it's hydrocarbons. So to blow that up a little bit, if we think about that beam of light coming in, that we get one wave that goes out and it just bounces through above the surface of the crystal and it touches that condensed fluid. And so that condensation absorbs that evanescent wave, and we watch that light beam gets attenuated when that condensation, if it's the hydrocarbon wavelength, the light beam gets attenuated when hydrocarbons are getting condensed on the surface. And if it's water, the light beam, or if it's the water wavelength, when water condenses, we see attenuation of that one. There's actually a little bit of overlap, and the software takes care of all of that. But from a conceptual purpose, the simplest way to look at it is saying one wavelength only reacts to water, the other wavelength only reacts to hydrocarbons. The evanescent wave penetrates actually a very short distance into there before it bounces back. And so that's why we generally draw it as just this little knob above the surface, if you like. It's all to do with the electric fields and how light is actually an electromagnetic wave, and chemicals, materials have electromagnetic properties to them, and it's how those things interact. Really understanding the fundamentals of how that interaction works isn't the important part here. The important part here is to realize that by using the way this interaction happens, we can tell whether the fluid that's sitting on the surface is water or whether it's hydrocarbons. So when we get a fluid come and lay down on this surface, as soon as it starts to show up on there, that wave is touching it, and it can say, well, is it absorbing it the way water does? If so, I've just hit a water dew point. Because remember, we start out with this crystal warm. There's no vapors there. If I started to cool this crystal down, when I hit the dew point temperature of the room I'm in, or if I was to breathe on it, the air that comes out of my lungs is moist because I'm at around 100 degrees F, 98 F. And so that moist air touches it, condenses on the cool crystal, we see a water dew point. If there's hydrocarbon vapors there, we see a hydrocarbon dew point. The big advantage that CEIRST provides us is that unlike other dew point analyzers, there's a number of other dew point analyzers, even automated dew point analyzers. This one will allow us to tell the difference between a water and a hydrocarbon dew point. Many of the chilled mirror techniques use just scattered light, and they say if there's liquids on the surface, I'm going to detect there's a liquid there. And the assumption is often made, well, water is going to be my first dew point, or hydrocarbon is going to be my first dew point. This technique allows us to actually tell which dew points we're hitting. We can cool it, we can hit that hydrocarbon dew point, say if the hydrocarbon dew point is 40 degrees F, or 8 degrees C or whatever, 5 degrees C. And if we cool it some more, we can hit the water dew point. So we can get both the water and the hydrocarbon dew point off of one measurement. The fact it's a non-metallic mirror means that we don't have to worry about issues. This saves us from problems with corrosion and contamination. So metallic mirrors, we worry about corrosion on surfaces. Can we keep them clean enough? Sometimes people will use alumina for this, and the oxide layer on aluminum is porous, so now things can get trapped in there. Sapphire is one of the most inert materials we have. Very hard, very chemically inert. We don't have to worry about passing the beam of light through the gas. The light stays in the crystal all the time. The crystal stays, this crystal is going to stay perfectly clean on the inside all the time. Sure, it could get contaminated on the surface, but the inside's going to stay clean all the time. If we're using a conventional light scattering technique where the light source is external to the surface and it has to shoot through the gas, if we get any contamination on the surface or on the sending unit, whether it's an LED or a laser or whatever, those are both going to affect our measurements. Here, the light stays inside the crystal, so the only thing we have to worry about is keeping that crystal surface clean. The fact we can separate the water and the hydrocarbon dew point lets us know exactly which dew points we're hitting. So if we buy a water dew point analyzer, it's only going to measure water dew point. If we buy a hydrocarbon dew point analyzer, it's only going to measure and tell us a hydrocarbon dew point. If we put both wavelengths in and use both measurements, we can tell the water and the hydrocarbon dew point simultaneously. Here we just show a number of pictures. It just shows some typical installations. It's a fairly simple installation. In Canada, of course, because it's cold outside, we're probably going to put this in a heated enclosure of some kind. We're not going to expose it to completely the elements. In the US, you can see installations that just go outdoors. Depends on the ambient conditions. We can put multiple analyzers into one cabinet. They're not very big. They don't take a lot of space. You know, they don't have a big heat pipe hanging off the side of it. They're fairly small, compact. ZEGAZ has done a wonderful job with their thermal management and how they can control the cooling and separate that and dissipate that heat as well. It's also available as a portable unit. So you can see one here, just sits in a little suitcase. You can run this out to the field, do water and hydrocarbon dew point measurements right out in the field. Full graphical display on the portable, and you can start to see which dew points you're hitting and make those as a field available measurement. From a specification perspective, one limitation is how low you can go on the dew points, because the thermoelectric chiller can only cool you down so much. And the thermoelectric cooler can take us about 50 degrees C below ambient. So in a 20 degrees C ambient means you can measure dew points down to minus 30 degrees C. So typically we say dew points to minus 30 degrees C. We can measure those dew points to plus or minus half a degree C accuracy, and that's for both the water dew point and for the hydrocarbon dew point. Again, those come out as two separate measurements telling us which dew point did we hit at which temperature. From a Canadian perspective, CRNs are important things. CRNs are done for 2,000, are available for 2,000 PSIG operation. Obviously in pipeline gas, what we're typically gonna see is typically 600 PSI to maybe 900 PSI. All the systems that go out are tested to 6,000 PSI. So kind of a summary of this is to say that the ZEGAZ Instruments technology, again, if you go back, say, again, I really liked Chelsea's question of why do you work with certain technologies? How do you pick them or whatever? The ZEGAZ technology is unique. Saurabh is on. He's a very brilliant guy who came up with this whole thing of using different types of spectroscopy to separate those two dew points. So it's a unique technology. Using this evanescent wave technology is, I believe, the only dew point analyzer that's doing this. It uses a spectroscopy side to separate those dew points, does those to high accuracy, and it's a true dew point measurement. It's not a calculated dew point based on an equation of state. It's a true measurement of at what temperature did I see condensation at. And I think, Scott's going to probably do a follow-up after this and send you out some brochures just to let you know kind of the products that are available. It's available as a water dew point only, a hydrocarbon dew point only, a mixed water and hydrocarbon dew point, and as a portable unit. And so depending on the measurement requirements that you have, we can address any of those measurement requirements with this technology. I'm going to pause for a minute here. I know I get accused of sucking all the air out of a room when I talk, because I just go and go. Any questions along the way that we want to address?
We have one on the chat there, Phil. What is the frequency of measurement?
Sorry, what's the fastest you'll go at? I think it's actually fairly quick, but 6 minutes, is it? Or Miriam? You guys know better than me.
Hi, this is Miriam. It depends on the ambient temperature and your dew point. So it's anywhere between 2 to 12 minutes. If your ambient is close to your dew point, of course, it's going to take less time for the crystal to cool to the temperature at which the dew point shows up. So if your ambient is very high and your dew point is very low, then it'll take longer. And I'm going to make a correction here. The lowest detection limit for our analyzer is actually minus 40.
Was it minus 40? Okay.
Yeah.
Sorry, I must have gone off of an old set of specs. Thanks, Miriam.
No problem.
There's another one on here too.
No cost for the portable unit. We like to talk about costs separately. Scotty can follow up with you on that one. It's cost effective. Certainly, it's certainly a cost effective solution. Because again, it depends a little bit. Currencies. We're sorry. Oh, that's Mike. Sheila. Hey, Mike. How you doing? Yeah, we'll talk to for you guys. It would even be special. Mike's with sulfur experts, and we do a lot of work with those guys. And no, they're ex-Western research guys, so they usually get a deal from us. We'll talk with you about that one, Mike.
In terms of cost, I'd like to add something here. The cost of ownership is much lower than other technologies available in the market for dew point measurement, simply because this is very low maintenance. You would never have to clean your mirror, change the mirror. You don't have to calibrate. Again, another advantage with about these units is that no calibration is needed. Because the temperature is the dew point is the temperature at which gas turns into liquid, and the thermistors that detect the temperature at the surface of the crystal, they come to us calibrated, and they keep their calibration for basically forever. So you don't need to calibrate these instruments. Whenever in doubt, you can use pure ethane, 99% pure or better, and do validation. Just because the dew point curve of ethane is pretty well known, you can use that and measure the dew point of ethane at different pressure points. If it falls on the graph, you would know that the whole system is working fine. So that's, we do validation, no calibration is required.
Yeah, chilled mirror is basically considered a first principles measurement of dew point. So it's what other things get calibrated against. And yeah, what you're really trying to do is just validate, do I hit the dew point when I expect to? And we do that with just running an ethane standard. So for Mike's application, I mean, for the sulfur experts application, they're looking at going out in the field in different places. So the advantage of this, you don't have to bring calibration standards with you, and you can do a first principle dew point measurement.
Got a couple other questions here now, Phil, too.
Main concerns for sample conditioning, extractive lag times, etc. So main concerns for sample conditioning are typically whether you have things like compressor pump oil carryovers and things like that. So generally in the sample conditioning system is fairly simple. Coalescing filters out in front of the analyzer, there to particularly just take out heavy oils and things like that. If you have amine carryover, liquid glycol, or compressor oils, that's what we want to prevent from getting into the sensor side of things. Because it operates at high pressures, we tend to use very narrow bore tubing. So we tend to use 1/8 inch and 16th inch tubing because we're running everything at high pressure. So to minimize that extractive lag time, we want to keep our sample system volumes down. So ideally, and you'll see kind of in some of these pictures, the ideal thing is to mount this out if it's going to be in a box like this, to mount it out as close to the sample point as we can, try to keep that sample transport line length down so we get faster response times. And then we also have a question about wavelengths that are used. Miriam, do you guys usually talk about which wavelengths you use, or is that considered private, or Saurabh?
Yeah, can you hear me?
Yeah, I can, Saurabh.
Okay, very good.
Nice to hear you.
So let me shed some light on that. First of all, we don't talk about the wavelengths. We use multiple wavelengths. It's not two separate detectors for HC and water. Mm-hmm. What we use a method that we internally call spectral slicing. So we use multiple detectors with not a specific wavelengths, but a number of different wavelengths on each detector. And then we go through a software process that resolves this. It's very similar, if you will, to the process that human eye uses. We have only 3 different types of detectors in the human eye, but yet we can resolve thousands of different colors. It's a very similar process. We don't talk about specifically which wavelengths we look at, but it is multiple wavelengths and multiple detectors.
Thanks, Herb. Okay, under what conditions would a validation not match the expected curve, and what self-diagnostics are built in? The conditions, I think, and Saurabh, you can certainly jump in here as well. But I think the conditions are typically going to be if there's contamination on the detector. If we've gotten things like pump oils or some material, the entire principle really is around the idea that if we've got a natural gas sample that wants to be in the vapor phase, and we cool the detector, we'll get condensation on the surface. And when we let the detector warm back up again, that condensation will evaporate away again and leave the surface clean. If we get something onto the detector which does not evaporate away again and leaves a film on that surface, then we can start to see some bias in the measurements. Often it can be cleaned just by running high purity propane or something through the cell and clean that material off, because it'll dissolve basically into the liquid propane. Saurabh, other conditions where...
Yeah, let me, so first of all, at the beginning of every cycle, there's a self-diagnostic check that will detect whether or not the crystal is clean enough to start a cycle, a measurement cycle. If for whatever reason, let's say you have filled the measurement cell with compressor oil, the unit actually recognizes that and will not start a cycle, and actually will send a prompt for cell cleaning that can be done. Now that condition with good sampling system that Insight Analytical does and our standard sampling system, there are filters that should remove compressor oil or things of that nature. But if that condition happens, the self-diagnostics will detect it and will not allow it to run, and will prompt the user to actually take care of the unit. If under 99.9% of the conditions, if a cycle starts, it means that all the diagnostics have passed and it can start the cycle. So there would be very, very very unlikely that the system would start the cycle and not detect the correct dew point. I do want to add one thing regarding the crystal itself. The crystal is actually an amalgam of 3 different materials that we actually designed here and gets fabricated for us at a local crystal growth facility. And one of the conditions, each individual one would not be sufficient to have the combination of the properties we want. But one of the things that's built into it is a non-stick property for the crystal that very, very few things will permanently attach to it. Actually, most contaminants will drip off of it because of the one of the ingredients that we use in the fabrication of the crystal. So it is not, it's not glass, it's not sapphire, but it's a combination of different materials that get fabricated at the crystal growth facility.
Thanks, Saurabh. I have a question from Larry. Do you generally recommend that the system be configured with ethane validation gas and propane cleaning gas? Generally, no. I mean, we've typically seen systems run in the field for extensive period of times. Again, it's a little bit can be dependent on what you think the quality of your sales gas is. But if it's pipeline quality gas, we typically don't see a need to that, especially if there's a good sample system in front to get rid of the compressor oils.
To add to that, we've had units running for 8 years in off of good pipeline quality gas without any issues. Yeah. We've also had units that, when they went into service 3 weeks later, they were filled with compressor oil. So it really depends on the quality of the gas, as Phil mentioned.
Right. And things that are done in the sample system. If you're aware, it's important to kind of try to be aware of whether you have potential issues with things like compressor oil and design an appropriate sample system. You may decide to suffer a bit on response time and put larger coalescers in to try to protect the device better. Again, it all depends on what you really need for the response time. I think we had a question or a comment earlier that if the water in the hydrocarbon dew point happen, or if there's already water there, that you won't see the hydrocarbon dew point. And I think that in most cases, water content in natural gas is pretty low. It's hard to wet the whole crystal all at once before you hit that hydrocarbon dew point as well. Saurabh, any comments on, is there a maximum differential between the water and the hydrocarbon dew point?
In theory, there is. In practice, there isn't. In theory, the maximum differential is about 50 degrees. But because the gas flow through this unit is very, very little, what will happen, even if water comes out, basically water has to come down so much that the gas would fill with liquid. And even if you have, we've had these units running on wellhead gas, and even in those cases, there is not enough water to actually fill the gas cell. So in theory, yes. In practice, no.
Okay. Cool. Any other questions? Sorry, if you see me always looking down on this side, it's because I have the chat on another computer on this side. That's why it's not like I'm trying to look away from everybody.
There is another one on there, Phil.
Oh, is there?
Yeah.
Oh,
sorry, that was directly to me. Just asking if there's a risk of unacceptable liquid cooling in the cell with high dew points.
I'm not sure exactly what they mean by that. I think that if there's, I think if you have a very high dew point, you'll hit, I guess the important thing is the analyzer has to be in an environment that is above the dew point of the gas that it's trying to measure. So if you have an application where, let's say you're trying to measure a 35 degrees C dew point, the entire analyzer and cabinet is going to have to be kept hotter than 35 degrees so that there'll be an opportunity to chill the mirror to get to 35 degrees and see that dew point.
If I could add to that, yes, that's generally true for all analyzers.
Certainly.
If your dew point is above the ambient conditions, you're basically having two phases coming into the analyzer, and regardless of what the analyzer is, that will create issues. If the question was about, that we cool too much, the end condition is the detection of the dew point. So once the dew point is detected, it stops cooling and it will go back to near ambient conditions to start the next cycle. So there is no runaway cooling, condition.
Right, and this is why Miriam was saying that, if your dew point is close to the ambient temperatures where the crystal starts at, then you'll hit that dew point, sense the dew point, stop that cooling cycle, and be able to let the crystal start warming up to get to the next cycle. So your response time can be faster when you're very close to the dew point. Hank Lee once asked the same question again, except from the other side now. Is it water first? If it's hydrocarbon first, both of them are the same answer, I think, Hank. There's not a lot of flow there. So as the crystal cools, parts of the crystal will have water on it, parts of the crystal will have hydrocarbons on it, and you'll be able to detect both dew points.
Yes, it will. It will detect both dew points because, again, when the hydrocarbon condenses out, it's not all of the gas that's condensing out. Right. It's the trace heavy components, and those are typically very, very low concentrations, and they do not stick to the crystal. They do condense out, trigger the signal, but if there is anything more than micro droplets, they will slip off and they will not permanently cover the crystal.
This is the whole advantage of that non-wetting surface, basically, that you were talking about, Saurabh.
Exactly. Yeah, and there is a question regarding the NIST standard.
Yes,
and it's a very important question, to be honest. So first of all, our instrument was tested at NIST, and there's a report available from NIST. They tested it against their multi-million-dollar chilled mirrors. But in essence, whenever you take an instrument, a moisture measurement instrument, and you take it to NIST for testing, you know what they tested against is a very, very expensive chilled mirror instrument.
Right.
So the measurement is a NIST standard in itself. Of course, we submitted our instrument as well, but the chilled mirror method is a first principle standard method that other instruments get tested against it. And it's because, it goes to back to the fundamental laws of physics, that why it's a standard. but it's a long discussion.
It's kind of the definition of dew point. Everybody else or other instruments, things that measure water content, like a tunable diode laser or an aluminum oxide crystal, aluminum oxide sensor, they calibrate themselves against chilled mirror devices to determine whether they're doing dew points correctly. So,
yeah, absolutely. But this instrument was tested at NIST, and there is a report available if anybody's interested.
well, I appreciate all the questions. That's I always like when we get lots of questions. Is there anything else that we haven't touched on that you'd like us to touch on about this device? Saurabh, Miriam, anything you think I missed that I should have talked about?
I do want to talk about the applications for a second. I think it's important for the customers to understand the applications. So one of the things that's happening, and we see in our sales as well, is the biogas application. We're seeing a lot of people in the because biogas is growing worldwide. We see a lot of installations at biogas sites, and particularly power plants, because these creation of liquids within the turbines can create a lot of what I would call a multi-million-dollar worth of damage to the turbines. We see a lot of installations in the power plants. These are in addition to the traditional pipeline custody transfer and whatnot. And the second point I want to make is that for all the reasons that you want to measure moisture, corrosion, bacterial growth, hydration, hydrate formation, all the reasons that you want to measure the moisture content, they really relate to the dew point. Mm-hmm. The reason is that it's only when formation of liquid water happens that water becomes important. And measurement of dew point is actually a better way to control pipeline operations than measurement of water content. And that's why still worldwide, a lot of these tariffs are written in terms of dew point rather than water content.
Right. And places that didn't write them in terms of dew point did it because they didn't realize that there was an online method of measuring dew point available. The PPM water analyzers had been around for a while, and so they said, well, we'll write our tariff around a concentration, but realistically, as Saurabh is saying, the reason we measure water is to prevent hitting a dew point.
Absolutely, and that's a very important point, that it is really liquid water that creates all the issues, and that's why it was written originally way back when it was dew point. Then in the US it changed to water content because there were no dew point equivalent available. Worldwide, they're still in terms of dew point.
Right.
And in US, I don't know about worldwide, but in US, sort of the measurement of last resort when there are conflicts is still a chilled mirror, because it is that first principle measurement.
And most places that don't have an automated water dew point analyzer have a manual dew point tester there, which again, we could see that being easily replaced with the portable for doing dew point testing.
Yes.
All right, that's going to wrap me up on that. I'm just going to give a quick, again, I got to do my little sales pitch at the end here. So a little bit about some of the other technologies we work with. We work with JP3 measurements, measuring natural gas liquids and condensates, crude composition. We use this for crude oil blending, for measuring C3 plus and C5 plus streams. ZEGAZ, obviously, that we spoke about extensively today. We also work with spectra sensors, tunable diode laser technology for H2S, moisture, and oxygen. We work with Barbon and use their oxygen analyzers. We've done oxygen, water, oxygen, hydrocarbons, especially for things like VRUs and flare gas. In the US, they do more oxygen and pipeline gas because their spec is much lower. They have a spec of 100 parts per million in the US. We have one of 4,000 parts per million in Canada for oxygen and natural gas. But certainly for vapor recovery units, flare gas units, these are a fantastic little oxygen analyzer. No moving parts, low maintenance, again, optical technologies. Work with universal analyzers, especially with their reflux samplers for process measurements. Recently, we brought on the Hawk measurement systems line, and Hawk has brought a whole bunch of new technologies to us. So I want to talk briefly about that. multiple different types of level sensors. So we can do ultrasonic, which has certain advantages, and depending on the frequency, we can do a very high frequent or high power ultrasonic, which can push its way through particles. Jessica's on. She recently did an install at a place that was making wood chips or basically making wood pellets. They had a lot of wood fines around over the top of their chip levels, and other level sensors would have difficulties with the background. These ultrasonics can be great for that. We do a fiber optic pipeline sensing. So pipeline integrity, 40 to 80 kilometers of pipeline with fiber optic wrapped around it. We can tell if there's a pipeline leak. We can tell if someone's starting to try to dig beside the pipeline. We can talk a little bit more about that on the last slide, or last part of this slide as well. Sorry, I realize I'm rushing a bit because we're short on time. Centurion guided radar sensors. We can, again, we can go into high temperature applications. We can measure between or small gaps in places to get to the level below it. Another type of level sensor with very specific applications. We do a sonar sensor. We can do tailing ponds in the mining industry or in the oil sands, and look to tell both the water level, where it hits the first level, we're starting to get flocculation, so particulate is starting to mix with the water, to the absolute solid levels below that. So we can do tailing pond depths and where we're starting to get flocculation of the particulate at. Again, in the mining industry, they'll sometimes put clarifiers in there, so we can use those in those applications as well. From simple water measurement, the mini wave is kind of a simple, just a water tank type device. We can use this same technology, microwave technology, to do collision detection, to look for block chutes, multiple applications. We're going to do a whole webinar about this in about 2 weeks from now. But next week, we're going to do one a little bit more about this fiber optic spectroscopy thing. So we can take a fiber, pulse a laser beam down it, and how the laser light bounces back tells us information about the strain that's in the fiber, the temperature distribution of the fiber, and whether there's vibration in the fiber or not. So we can use this on things like conveyor belts to watch for idlers overheating or starting to vibrate, tell you where you're going to get a conveyor belt breakage, or we can put it on a pipeline and we can say, well, if there's a natural gas leak, you're going to have vibration due to the leak and local cooling, and we can use this for leak detection along an entire length of pipeline. So we'll be doing a whole seminar on that next Friday at 10 a.m. So the next webinar we're doing is about fiber optic sensing, pipeline integrity, conveyor monitoring, even security. Wrap it around a fence and you can tell if someone's climbing the fence. Just a bit again about our systems integration. This slide's kind of animated and just shows some of the systems that we put out. Composite samplers on pipelines, to full automated sample systems, to analyzer buildings and shelters, to toluene flushes for spectrometer systems. Again, some more automated sample systems. Really, my point here is we view it as kind of no job's too big or too small. We like doing systems integration. We're good at it. We bring a lot of experience to it. And we run full-time service. We support everything that we sell. We make sure we go get all our service guys trained on, and we serve it directly out of Alberta. So in summary, Insight brings a strong measurement-focused applications in the oil and gas industry. We run full-time service out of Grand Prairie, Edmonton, and Calgary. Most of our team has a strong, decades of experience in analyzers, analyzer sample systems, and shelter designs. So if you have an integration project you're looking at, if you're looking at putting something like a ZEGAZ in and want it as part of a full analyzer shelter, we're happy to do all that work as well. If you want more information, you can check out our website. You can follow us on LinkedIn or contact Scotty or myself, and we'd be happy to get you more info. With that, I'm going to wrap this up unless there's any other questions. Again, bunch of people on here that I recognize, and it's a pleasure to see. So thanks, guys, for showing up. It's always nice when I get people I know here, and kind of feels like actually getting out to a conference, except we can't have a beer after this. So we'll have that beer soon. Thanks again, everybody. And yeah, someone asked about the recording. Yeah, we usually try to, we're trying to get these up onto YouTube, and we'll send you links to the recording in case you have a colleague that you would like to have meet it, see it. And thanks again for coming, everybody.
Thank you so much, Phil.
Thanks, Miriam. Thank you for all your help. You too, Saurabh. It's great having you guys here to help with questions.
Thank you, Phil. Great job. Thank you.
Yeah,
Very
thanks.
informative.
Yeah. Oh, there's Bill down there. Is Valerie, is that Valerie Mertens from the Netherlands? Well, maybe she's not going to answer. Thanks for coming, Reiko. Cool. All right, I think I'm going to wrap this up and close this meeting down. So I'll stop sharing my screen now. And soon you guys are all going to, anybody who's left is going to get kicked. Thanks again, everyone.